Okay, well, this is lecture 3 in algebra. And let's start by
Excuse me,
asking
Professor.
if there are any questions about either anything we covered in the lectures last week or in the homework that is due tomorrow, I guess.
Hello?
Yeah, go ahead.
Professor, I see the homework on my screen. Are you going to go over it right now?
I said it's due tomorrow, but I said I'm happy to answer questions about a couple of the problems if there are any. Otherwise,
okay,
I'll go
okay.
over it on Wednesday.
Okay. Yeah, I think Wednesday is better.
Yeah, okay.
Thank you.
Okay, so we will start. So what we talked about last week was first a little bit about sets, and then an introduction to proving results in mathematics using mathematical induction. And let's see. So we had talked about sets, and we had talked about mathematical induction. I want to say a little bit more about sets, and in particular, the notion of a relation on a set X. So in general, if we have sets S and T, the product of S and T is a certain set, S times T, which consists of ordered pairs, S comma T, little s, little t, where S is an element of S and T is an element of T. So for example, we have the plane, R2. So this is what you learn when you're doing calculus. You have a function y equals f of x. A point in the plane is just an ordered pair x, y, where x is an R and y is an R. So R2 is just shorthand for the direct product, the product of the sets R cross R. Right? So you're really very familiar with this idea of taking the product of two sets. In general, we would write S squared as S times S. That's just the case S equal T. And in general, we could also define the nth product, S to the n. S times S times S times S n times, and this is a set of n tuples, S1 comma S2 comma S3 up to Sn, where S1 is in S, in fact, Si is in S for all I going from 1 up to n. So S squared is a set of ordered pairs, and in general, S to the power n is just a set of all n tuples. So that's the notion of a product of sets. And what is called a relation on the sets S and T let me give an example of a relation just. So on R, the real numbers, there's the relation X is less than or equal to Y. So if you have two real numbers, we can say they satisfy this relation if X is less than or equal to Y, like 3 is less than or equal to 7. So and in general, a relation on the sets S and T is simply a subset R of the product S and T. So the relation X less than or equal to Y on the real numbers is what? So it's a set of ordered pairs, X comma Y, where in R times R squared, where X is less than or equal to Y. It's all these ordered pairs where X is less than or equal to Y. So this is the formal definition of what is a relation in algebra. A relation on a pair of sets S and T is a subset of S times T. And a relation on S, if there's just one set, a relation on S is a subset of S squared, S times S. Now, a relation, there are lots of relations. Mathematics is in many ways a study of different relations. And there are certain properties a relation might or might not have. So here are three definitions. A relation R on a set S is reflexive if XX is in the relation for all X in the set. Now, another form of notation is if R is a relation on sets S and T, we write X squiggle sub R Y if XY is in the relation. So if X and Y are related, we write this X squiggle Y. So this is a standard kind of and very useful kind of notation for a relation. So with this notation, that R be a relation on a set S, which I remind you means that R is some collection of ordered pairs. It's a subset of S times S. So we say R is reflexive if every element is related to itself. If X is related to X for all X in the set. And I'll drop the R once I know what relation I'm talking about. We say R is symmetric if whenever X is related to Y, then Y is related to X. So a relation doesn't have to be symmetric, but if it is, it is. And third, we say R is transitive if whenever X is related to Y and Y is related to Z, then X is related to Z. Okay. So a relation may or may not be reflexive, may or may not be symmetric, may or may not be transitive. So let's look at some examples. Suppose we have the relation X less than or equal to Y on the real numbers. So X is less than or equal to X for all X in R means this relation is reflexive. Is it symmetric? So for example, 1 is less than or equal to 7, but 7 is not less than or equal to 1. So therefore, this relation less than or equal to is not symmetric. If one number is less than or equal to another, it doesn't mean that the second is less than or equal to the first. And if X is less than or equal to Y and Y is less than or equal to Z, then X is less than or equal to Z. So less than or equal to is a transitive relation. So this relation is reflexive, but it's not symmetric. It is transitive. And all sorts of permutations of this are possible. Consider here's another example. The relation X strictly less than Y is not reflexive, not symmetric, but is transitive. It's not reflexive because no number is strictly less than itself. It's not symmetric because 2 is less than 3. It doesn't mean that 3 is less than 2. In fact, it's not. But if 2 is less than 3 and 3 is less than 5, then 2 is less than 5. So this relation is transitive. Now, the nicest relations are the ones which satisfy all three of these properties. And what is called an equivalence relation is a relation that is reflexive, symmetric, and transitive. And the most important example is equality. So on any set S, the relation R, which is everything ordered pairs of the form x comma x for all x in the set, is an equivalence relation. Because first, by definition, x is related to x for all x in S. So that means this is reflexive. Second, if x is related to y, that only happens if x equals y, which only happens if y is related to x. So this is symmetric. And third, if x is related to y and y is related to z, this means x equal y and y equals z. That's what this means. And y related to z means y equals z. And if x equals y and y equals z, x equals z. So x is related to z, which means the transitive property is satisfied. So equality is the basic, simplest example of an equivalence relation on a set. What's another example? On the set Z of integers, 0, plus minus 1, plus minus 2, plus minus 3, and so forth. This is a set of integers. Let's say that x is related to y if x minus y is an even integer. Well, for all x in the integers, x minus x is 0 is even. So x is related to x for every x. And this relation is reflexive. If x is related to y, then x minus y is even. And so y minus x, which is minus x minus y, well, the negative of an even number is also even. So y is related to x, and the relation is symmetric. And if x minus y, if x is related to y, and y is related to z, then x minus y is even, y minus z is even. And then what? Well, x minus z is x minus y plus y minus z. So x minus z is the sum of an even number plus an even number. And they teach you in elementary school, the sum of two even numbers is even. So x minus z is even. So x is related to z. And this relation is transitive. So on the integers, the relation x related to y, if x minus y is an even integer, is an equivalence relation.
Excuse me, Professor. Quick question. Will you post?
Wait, speak up, please, because it's hard to hear you.
Oh, can you hear me?
Just barely.
Oh, I just wanted to confirm that you mentioned you will post the notes on Blackboard. Have you done so yet or not yet?
I will do that. I'm still editing them a little bit, but for what I'm doing this last week and this week and next week, I'll probably post them either tonight or tomorrow morning.
Okay, perfect. Yeah, just because it's a little bit blurry, it's a little hard to see because of the lighting and in the background.
Let me see. Wait a minute. Is that better?
Oh yeah, that's a little better. Thank
Yeah,
you.
okay, I'll leave it like that.
Perfect. Thank you.
In geometry, you have the notion of congruent triangles. Congruence of triangles is an equivalence relation. Because every triangle is congruent to itself. If triangle A is congruent to triangle B, then triangle B is congruent to A. And if A is congruent to B and B is congruent to C, then A is congruent to C. So congruence of triangles in geometry is an example of an equivalence relation. And we'll see lots of equivalence relations. Now, let's recall a partition of a set X is a set of subsets of X. Let's say X1, X2, X3, could be finitely many or infinitely many, such that they are pairwise disjoint. If you take two sets Xi and Xj, for I different from J, the intersection is the empty set. So this means that the elements common to both Xi and Xj, well, there aren't any. The intersection is the empty set for I different from J. And every element of X is in one of these sets. So X is the union of all of these sets. So the picture of a partition of a set, you have a set X, and you divide it up into pieces. That have no elements in common. So every element of the set is in one and only one of these subsets. So that is a partition of a set. And actually, from a partition, you get an equivalence relation. So, for example, let X be the union of three sets where X1 intersect X2, X1 intersect X3, X2 intersect X3. All three of these sets are empty. And we can define a relation on X as follows. For all X and X prime in the set, let's say X is related to X prime if X and X prime are elements of the same one of these three sets. Every element is in one of these three sets. We say X and X prime are related if they belong to the same subset of X. So that is a relation, and I claim this is an equivalence relation. So let me just write this down again. Let X be the union of three sets where x1 intersect 2, x1 intersect 3, x2 intersect x3. These pairwise intersections are all empty. Define R to be the set of all pairs XX prime, such that X and X prime are in the same one of these three sets. So I claim R is an equivalence relation. Well, first, R is certainly reflexive because X in the set Xi implies X is in Xi. I mean, that's sort of a tautology. And so X is related to itself for all X in the set. So this is a reflexive relation. And if X is related to X prime, then there is a set Xi with X in Xi and X prime in Xi. And so I can just write that down, same statement. X prime is in Xi and X is in Xi. And so X is related, so X prime is related to X. So therefore R is symmetric. If X is related to X prime, then X prime is related to X. So suppose X is related to X prime, and X prime is related to X double prime. There exists I with X in Xi and X prime in Xi because X is related to X prime. And there exists a J with X prime in Xj and X double prime in Xj because X prime is related to X double prime. But if X prime is in Xi and Xj, these two sets are disjoint, so they have to be the same set. So I equals J, and X is in Xi, X double prime is in Xi, implies X is related to X double prime. And that implies the relation is transitive. So whenever you have a partition of a set, you obtain an equivalence relation. And the converse is also true. Every equivalence relation defines a partition. So suppose that R is an equivalence relation on a set X. Let's define the equivalence class. So this is what I'm defining. The equivalence class of element X in the set is the set of all X prime in X, which are related to, such that X is related to X prime. So you have an equivalence, you have this equivalence relation on a set. Certain elements are equivalent to each other. If you fix an element X, the equivalence class of X is everything related to X. And I claim the set of equivalence classes is a partition of X. So that's the proof. Let's see the proof. Suppose we I'll write square brackets X, denote the equivalence class of X. So the union of all the equivalence classes, so X, so the relation is reflexive, implies X is related to itself, and so X is in the equivalence class of X for all X. So the union of all the equivalence classes is the whole set. It's the whole set. So what I have to show is that equivalence classes are disjoint. So the equivalent statement is must show if the equivalence class of X intersect the equivalence class of, let's say, Y is not empty, then the equivalence class of X equals the equivalence class of Y. So if I take these equivalence classes, they either are, if two equivalence classes have an element in common, then they're the same set. So proof. Suppose Z is some element which is in the equivalence class of X, intersect the equivalence class of Y. Then to say Z is in the equivalence class of X means X is related to Z. Which means Z is related to X by transitivity. Sorry, by symmetry. Z in the equivalence class of Y implies Y is related to Z. We have Y is related to Z and Z is related to X. Implies Y is related to X by transitivity, which means X is in the equivalence class of Y. That's it. Let me just make sure that I'm saying this all correctly. I want to prove that if two equivalence classes have a non-empty intersection, then they're equal. So If they have a non-empty intersection, then there's an element Z which belongs to both equivalence classes. So if Z is in the equivalence class of X, then X is related to Z. If Z is in the equivalence class of Y, then Y is related to Z. If X is related to Z, Z is related to X. If Y is related to Z and Z is related to X by transitivity, Y is related to X. Okay. Let me just stop at that point. So for every element X prime in the equivalence class of X, X is related to X prime. Because Y is related to X, from Y related to X and X related to X prime, we get Y is related to X prime. And so X prime is in the equivalence class of Y. So, I mean, this is something you have to go through carefully at home, but what I just showed is every element in the equivalence class of X is in fact in the equivalence class of Y. So the equivalence class of X is a subset of the equivalence class of Y. So if Z is in the intersection of the class of X and the class of Y, the class of X is contained in Y. And by the symmetry in this argument, because if Z is in the intersection of X and Y, it's in the intersection of Y and X. We also get that the equivalence class of Y is contained in the equivalence class of X. And if you have two sets and each is a subset of the other, then they're equal. So this is a nice argument in elementary set theory. If you look at the set of equivalence classes of a relation on a set, they partition the set. This is really an incredibly important fact in mathematics. And so we have a set X, an equivalence relation R on X, and what we write as X slash R is the set of equivalence classes of R. X is called X slash R is called the quotient set. Of the relation. So let's look at an example. Suppose we let X be the set Z of all integers and define the relation X is related to Y if X minus Y is an even integer. So, for example, what is the equivalence class of 0? The equivalence class of 0 is all integers X such that X minus 0 or X is even. So this is the class of even integers. 0 plus minus 2 plus minus 4 plus minus 6 and so forth. The equivalence class of 1 is all X, all integers X, such that X minus 1 is even. And that's exactly the set of all x such that x is odd. And this gives us all the numbers. Here we have the integers. We have the even numbers and the odd numbers. This is the equivalence class of 0. This is the equivalence class of 1. So we have the odd numbers and the even numbers. So the quotient set, Z mod R, that's this relation, contains two elements. Zero and 1, or the equivalence class of 0 and the equivalence class of 1. So the quotient set consists of two sets, the set of even numbers and the set of odd numbers. But there are only two things in this set. Everything in this set happens to be an infinite set of integers, but they're just two of them. So this is a really important example. And it's worth spending a lot of time thinking of this. Here's another example, which will probably be part of the homework for next week. On the set of integers z, define x is related to y if x minus y. See, in the previous example, we said two integers are related if their difference is even. Even means divisible by 2. If x minus y is divisible by 3. So you should show this is an equivalence relation and show there are exactly 3 equivalence classes. The class of 0 consists of all the numbers that are divisible by 3. The class of 1 consists of the numbers 1, 4, 7, 10, 13, and so forth, and -2, -5, -8. And the class of 2 consists of 2, 5, 7, 10, 2, 5, 8, they go up by 3, 11, 14, and -1, -4, -7, -10, and so forth. So this relation, the two integers are related if their difference is divided by 3 evenly, is an equivalence relation, and there are exactly 3 equivalence classes, and there they are. Okay. Any questions about that? Okay. Now, there is a special kind of relation called a function. I mean, you spent all of calculus studying functions. You have, y equals x squared as a function. And I want to give a sort of more general notion of function, which is the following. I mean, informally, you think of a function, say y equals f of x. You have this box and you put in a number x, and out comes some number y, which we call f of x. We don't know what's going on inside this box necessarily, but you put in an x and you get a y. So one way to define a function in a very general sense is as a special kind of a relation. So recall that a relation R is a subset, a relation R on the set x cross y, on x and y, is a subset of the set of ordered pairs, x comma y. So that's a relation. And a function is a relation that satisfies the following properties. So for every x in the set x, there is a unique y in the set of y such that x comma y is in the relation. Let's call this relation F instead of R. So a relation F is a function if for every x in x, there's a unique y in y, such xy is in F. And our standard notation for this is that y equals f of x. And the most important operation on functions is what is called composition. So that x, y, and z be sets. So let f from x to y be a function. This means that f is some subset of x times y, it's that relation. Let g contained in y cross z be a function. So what we have is this function f contained in x cross y, and we have a function g contained in y cross z. I want to construct the composition of f and g. This is a function h from x to z. So here we have f from x to y and g from y to z. I'm going to put them together and get a function h from x to z called the composition. And there's a very simple definition of this. So h of x is what? Well, if you take x, there's a unique y such that xy is in this function f. So f of x is in y, and g of f of x is in z. So this is the definition of this composite function. We usually write it as with a circle, g composed with f. So we can draw a picture of this. We have x going to y with this function f. F takes x to y. we have a function g from y to z, and the composite g composed with f goes from x to z. So you did this in calculus over and over and over again. You learned the chain rule for differentiating the composite of two functions. So you are certainly familiar with this notion of composition. If f of x is, for example, x squared plus 1, and g of x is cosine x, then f composed with g of x is f of g of x. Sorry, I want to do it in the other order, just to follow this picture. G composed with f of x is g of f of x. That's g of x squared plus 1. That's the cosine of x squared plus 1. Yeah. That's the composite function, g composed with f. And here is a very important property of composite functions. Suppose we have three functions. We have a function f from x to y. We have a function g from y to z. Suppose we have a function h from z to w. Now, I can compose f and g, and I get a function gf from x to z. And I can compose this function from x to z with h, and I get a function h composed with g composed with f. So I have this function from x to w. Now, I could have done this differently. I have y goes to z and z goes to w. If I compose these two functions, I get a function hg from y to w. And here I have a function x, f from x to y, and then hg from y to w. So I could compose this and this, and I get a function hg composed with f. So depending on what order I do my compositions, I get two functions from x to w. I have the function h composed with gf, and I also have the function hg composed with f. And the very important theorem says that these are the same functions. H composed with gf is hg composed with f. So mathematicians like pictures like this. Whenever you can draw a picture, you understand what's going on a lot better. So what is the proof of this? So suppose we let x be in the set x. So then hg composed with f applied to x is hg of f of x. hg of f of x is h of g of f of x. G of f of x is gf of x. And h of gf of x is h composed with gf of x. So hgf applied to x is the same as hgf applied to x for all x. And that's the proof of this theorem. Again, all of this will be in the notes that I post, and you really need to spend a decent amount of time going through this carefully and making sure you understand what's going on.
Professor, can you hear me?
Yeah.
Okay. Question. So is this still part of chapter 1? All these notes? In
Yes.
the textbook? Okay.
Yeah.
Gotcha.
Except that the exposition in the book by Alan Clark is much more concise than what I'm doing. So I'm putting in a lot more details. And now there's a very general construction that we use all the time in mathematics. Which is the following. Let me just introduce a few more words because they're useful. Suppose we have f as a function from x to y. So you might think of this as x and this is y, and you have this function f going between them. So if you take a certain set A in x, what is called the image of A is the set of all things of the form f of x, x in A. So you take an element here, it gets mapped to something over in the set y by this function f. This is contained in y. So from A, f of A is the image of this set A in y. If you have a set B in y, so this is for A contained in x. Suppose we have a set B contained in y, what is called the inverse image of B is the set of all x in x such that f of x, so if you take a point x in x, it gets sent to y, some x's actually end up in the set B. So if you look at all the x's in x such that f of x is in B, this is what is called the inverse image of B. So you start with a set B, and you look for all the elements of X that get mapped into B. There may be elements in B and nothing in X gets sent to that element. That's okay. It might be, in fact, that nothing in the set X gets mapped into B at all. This could be the empty set. That's perfectly all right. But for any set B, the inverse image is all the elements of X that get mapped by the function f into B. The image of A is sometimes denoted f of capital A, and the inverse image of B is sometimes denoted f minus 1 of B. This is just some notation. There's certain kinds of pictures that are used a lot in mathematics, especially in algebra. So suppose we have a function, we have sets X, Y, and Z. We have a function f from X to Y, and a function G from Y to Z, and a function H from X to Z. So this diagram looks like a triangle. And this is called a commutative triangle. See, how can you get from X to Z? You can either go directly through H, or you can go this way, passing through Y. And if these are the same, no matter which path you take, that means if G composed with F equals H, this is called a commutative triangle. And the beautiful example of this, which brings together many of the things we've discussed today, is in the following theorem. So suppose f from X to Y is a function. That script R be an equivalence relation on X that X slash R be the quotient set of equivalence classes on X. We define what is sometimes called the canonical function pi from X to the set of equivalence classes by pi of X is the equivalence class of X. So let me just draw a picture of this. Here we have the set X, and on X, we have the different equivalence classes. And here we have the quotient set, which is the set of equivalence classes. And we have this function pi, which sends an element X to its equivalence class. Suppose there's a function f from X to Y such that if X is related to X prime, then f of X equals f of X prime. So if you had two elements, X and X prime in X, the function f, if they're related back in X, the function f sends them to the same element over in Y. So there is a unique function f tilde from this quotient set into Y such that, so here's our picture. We have X, we have the quotient set and this canonical map pi. We have a set Y and a function f, which satisfies the property that if X is related to X prime, then f of X equals f of X prime. And the theorem says there is a unique function f tilde from X, from the quotient set to Y, such that this diagram commutes. This is a commutative triangle. That is, f tilde pi equals f. So we have a commutative triangle. Well, so the proof is define f tilde of the equivalence class of X to be equal to f of X. If the equivalence class of X equals the equivalence class of X prime, then X is related to X prime. And so f of X equals f of X prime, because that was our condition on the function f. If X is related to X prime, f of X equals f of X prime. And so f tilde of X, which is equal to f of X, is equal to f of X prime, is f tilde of the equivalence class of X prime. So this is one of these things that is very, very, very easy to write down. But you actually have to spend a fair amount of time thinking through what all of this means. There are a lot of mathematical ideas embedded into this. So what we've talked about in the three classes we've had so far, sets, relations, functions, mathematical induction, that is the content of what will be chapter 1 in the notes that I post. And the next chapter will introduce something that's called a group. And in the next chapter, we study two different examples of groups, and one of them involves matrices. So if you are not familiar with this, I will tell you right now what is a matrix. Matrix is the singular, the plural is matrices. Let's start with the simplest, the 2 by 2 matrix. It's just a square array of 4 numbers, A, B, C, D, written like that. That's a matrix. And there's lots of different notations. We could write this as A11, A12, A21, A22. See, when you look at this matrix, you think of this as being the first row and this as being the second row. And this as being the first column and this being the second column. So here, Aij means the number, the coordinate in row I in column J. And there's some arithmetic you can do with matrices. The easiest thing is addition of matrices. So if you have 1, 2, 3, 4, and 5, 6, 7, 8, and you add them, you just add the corresponding coordinates. So first row, first column here is a 1. First row, first column here is a 5. You put in 1 plus 5. First row, second column, 2 plus 6. Second row, first column, 3 plus 7. Second row, second column, 4 plus 8. So we get the matrix 6, 8, 10, 12. That's how you add. You subtract just by subtracting coordinates. -4, -4, -4, -4, as it turns out. That's subtraction. If you take any matrix and you add the matrix, which is all zeros, you just get back the same matrix. And if you take any matrix and you add the matrix, which is the negative of each of the coordinates, you get back the 0 matrix. So the addition of matrices and subtraction of matrices, that's pretty easy. Matrix multiplication is a little bit trickier. Suppose I have A, B, C, D, and I multiply by E, F, G, H. So what you do with matrix multiplication, it's sometimes called multiplying a row into a column. So here's the first row. Here's the first column. When you multiply a row by a column, you get multiply the first coordinates and the second coordinates and add. So first row, first column, when you multiply them, that goes into this 1, 1 position over here. This is the first row, second column of the product. You take the first row times the second column, AF plus BH. For the second row, first column, you take the second row multiplied by the first column here. And second row, second column, CF plus DH. So this is how you multiply matrices. You take any matrix A, B, C, D times the matrix 1, 0, 0, 1. You just get back the same matrix. This matrix is usually written I for the identity matrix. So let's look at 2 examples. Suppose X is the matrix, I don't know, 1, 2, 3, 4, and Y is the matrix 0, 3, -1, 2. So when I multiply them, 1, 2, 3, 4, 0, -1, 3, 2, row into column, I get -2, 7, -4, 17. What about if I multiply them in the opposite order? So I get 9, 12, 5, 6. Completely different. So xy is not the same as yx. So this is really an important fact about multiplication of matrices. Order matters. Order doesn't matter when you multiply numbers. 2 times 3 is 6 and 3 times 2 is 6. You get the same thing no matter if you multiply numbers x and yx, you always get the same thing. But for matrices, it's completely different. The product of two matrices, x and yx, occasionally they'll be the same, but that's a rare, relatively rare thing. And typically xy is not equal to yx. So you can never assume that they are. So in the algebraic language that we'll talk about on Wednesday, this says that matrix multiplication is not commutative, but it's really important to recognize this. Again, we're going to spend a lot of time dealing with matrices, especially 2 by 2 matrices, which are the simplest in a certain sense. And when we learn the language of group theory, groups, an important class of groups are groups of matrices. That's what we'll be looking at in some detail at some point. Okay. Oh. So according to my count, we just did 18 pages of notes. That's a lot. And we covered a lot of material. Now, it may be if you've taken some advanced mathematics courses beyond calculus, you're very familiar with matrices and with sets and with functions and so on. But I don't assume that you've seen it before. That's one reason why I'm going through everything in some detail. And it really is important to learn this because this is the language of mathematics. This is the language when we discuss mathematical objects. And it's really important to become familiar with this. Okay. Any questions about this? All right. So I will make sure I post these notes. I'll try and do it tonight, actually, for chapter 1. This is what we've covered so far. And I'll try and get chapter 2 up as well. Okay. Again, there's homework that's due. It's always good to turn the homework in on time if you can. Also, if you do the homework and there are things you can't do and you keep thinking about it, I set up the Blackboard website so you can resubmit the homework as many times as you like. So if you want to add the solutions or correct the solutions to things that you did wrong, you're very encouraged to do so. You take your homework, you convert it to a PDF file, you go to the Blackboard website for the class, you go to assignments, you will see homework 1, and you upload your file to homework 1. And it gets graded and the grades are posted there on Blackboard, so it's easy for you to see. Do not email your homework to me directly. That's of no use to you because there's no way I can do anything with it on Blackboard. You have to upload your PDF to Blackboard.